even though this has nothing, has no direct support for loops or for conditions, it is quite possible to do so, and I think it's a very nice and flexible way to set up these quite complex systems. As a spin-off, and this is about the last sheet I have. As a spin-off, I realized that such a system could be useful in other contexts as well. One of my personal interests is water quality, and one thing you could do is run a whole series of computations deciding what location of a wastewater treatment plant could be to optimize water quality criteria, etc. For that you need, again, a large number of computations, and automating that sort of work is quite useful, because often these computations take hours, and you don't want to go in again and again and again. So automating that sort of thing is something I'm at the moment working on. There are quite a few problems to solve, because things like the variation in scenarios, a different location, different parameter values, all kinds of things may be possible, and I'm not quite sure how to manage that yet. But well, I'm working on it. Okay, thank you.
Trying to get away. Asha, question: did you think of or have a GUI program that's a dashboard kind of showing where in the status stream the various scenarios are?
Not as such. What I did was the script also writes, script scheduling the jobs also writes a log file. So from time to time I examine the log file to see whether new jobs have been scheduled or whether a job had finished and crashed, and so I could do anything about it. So nothing as formal as a GUI. Yes?
Now that you've made the connection back to a formalization based on tuple space, have you got any ideas that you might take the jobs themselves and wrap them in a script that would just autonomously pull the next job from the tuple space rather than having a switcher decide where to start a new job once formalization?
Yes, that's something you could do, yes, indeed. In this case I didn't really need that. It would have been a bit difficult because one program ran on a PC at over another institute. Then I had my Linux cluster, and my own PC was used to run the last stage, and then the results went back to Tino, so the other institute. But if you have a different kind of setup and things are more homogeneous, then certainly you can do that. Certainly you can have the one stage schedule the next stage. Yeah. Yes.
When you were developing your processes that you used for the computation,
Yes.
and you had to design it to work across the cluster, did you find that you had pieces missing that you could have used perhaps in Pickle that need to be developed in order to make things easier?
Yes. Yeah. One thing is, at some point in time, I had to use a shell script, and that's because scheduling the jobs, the actual scheduling on the cluster, was easiest using the shell script. And well, I'd like to formalize that sort of work, and I would like to take the opportunity of the web sessions to talk about that. Yes.
We do a very similar process with our simulation. Just going, we just swap nodes.
Let's do so.
Sign me up for the web too.
Okay. Don't we have someone else who does simulations with the Army? For the Army?
Sim.
Yeah, but where ours are rather different.
Oh, okay.
Well, the cluster we have has a few commands to monitor what's going on, and I use these commands to see what my jobs were doing. Yes, I think it's a Silicon Graphics. No, some grid engine, SGE. But it was easy enough to use using shell scripts and scripts. And since these programs last for days, I didn't have to have a high throughput of these things. If you come in the morning and just check the class status, then that's enough. Or I was a bit impatient and did it twice a day or something, but that's it. If you have a more dynamic system, so for a short time scale, then I can imagine that you want a GUI, which is present on the background. And gives you insight in what's going on every moment of the day. But with this, it was necessary.
I'm curious, have there been any models or simulations that you wished you could include that were not available on the cluster, that were more remote, that you still have in mind?
Well, these are all our own products, so they were available. I'm not sure, no. For this particular system, this was enough. On the other hand, I can imagine that while using Amazon servers could be another step.
Well, one could imagine weather simulations, for example, if that's
Yes.
a factor, if there's large storms are part of the scenario.
Yeah, well, in this case, in this particular case, we didn't use that sort of thing. The floods, as they run at the boundary, they are standard floods. What you can also do is model more than that and use weather predictions to model the amount of water coming into the river and have a more realistic or more realistic simulation. But in general, that's short timescales.
Does the breach model take into account that as the breach continues to last, it widens due to erosion?
Yes, it does. It does so using a few mechanisms. I haven't talked about that. If you're interested, I can explain a bit about it.
Of course I'm interested.
Okay. Yeah, sure.
Who uses the results of your work?
We are currently designing a control room, a flood control room, and the intention is to use this kind of model results to plan evacuation plans to see where you can have these extra dikes to confine the water. So it's a long-term strategy, but this kind of models, at least the high-level model, that would be used in short-term evaluations of the situation. Say there's a lot of rain in Germany, then you can expect a flood in Holland, and then you want to know what would happen if there's a dike breach somewhere. So that sort of models is being used right now to make this kind of predictions and to get people alarmed and in an active state to should such a situation occur.
What about on the ocean side? Do you have concerns about the global warming raising the water levels to a point where the dike systems are?
Yeah, sure. Yes, we have. I'm not involved with projects like that, but there are a lot of studies about how to strengthen dikes or to rearrange activities and people in these areas. Should we have large sea level rise the next couple of decades. And there have been studies in what Holland should look like in 2050 or even 2100. So it's all very difficult, and well, the future is interrupted, of course. It's very difficult to be precise about this sort of thing, but you can at least take a look at have a look at what alternatives you have. For instance, if I go back to this picture, this whole area. I myself live here, by the way. This whole area is below sea level, and one of the scenarios we've been looking at is, well, we can go on and on strengthening the dikes, but perhaps we should give up and move everybody over here, which is well above sea level. That's a very drastic measure, of course, but raising the dikes by 10 meters or whatever is also a very drastic measure. And in the end, you can't win. So these are alternatives that are being, well, discussed in informal ways. There are very long-term plans, but if you don't start now, when it is really necessary to take these measures, then it may be impossible to actually take them. So we are looking into these.
Good, because we're going to be there too.
Sorry?
We're going to be there too. In
Yeah.
2050, the Bay Area is likely to need dikes all around it.
Yeah.
Okay, so you're putting together a bunch of simulations, and it takes weeks, days to weeks to come to a scenario, 1 or 300 scenarios. Are they finding a way so that should we go here under these circumstances, have a situation plan, kind of pro forma evacuation plan ready? So they review and find a way?
Yes, well, of course, these are 300 computations and
Scenario.
300 scenarios. If you have an actual situation, then you want to have it much faster, of course.
That's right, so we use this pre-computation.
Yeah. Well, this was a very detailed model, and probably if you have a real need for an actual situation, you can using even more processes, a simpler model, either less spatial resolution or less resolution in terms of the hydrodynamics. So make it all faster. And I must confess that since I wrote this presentation, I was able to make these computations a bit faster by a factor of 3. One of the reasons for the slowness was that sleep on Windows is using a parameter in milliseconds, and on Linux it's using seconds. So when I realized that that was occurring, that was about a factor 2 in computation time. So nowadays, these computations take up to a week rather than weeks. Okay. I think we should continue with the next presentation, and Sean will tell you who that is.
Okie dokie. Sound right. Okay, OTK script for word fishing software.
Good morning, everyone. This is the first time for me to attend a programming conference, actually, because this is not my major. So I would like to introduce myself first, briefly. My name is Winnie Wang. I came to the United States 7 years ago from China, as you can tell. During the first 4 years, I was working on my PhD in computational fluid dynamics. To be more specific, is turbulence modeling. So I don't call myself a very professional programmer as you are, but I have learned a lot from you guys. So after I graduated, actually I have accepted a job as a support and consulting engineer at Pointwise in Texas. In this presentation, I used to just deal with parallel code written in Fortran and MPI, and I never used any small languages before my job. And for my job, most of the time, I don't program unless our customers want me to develop some specialized meshing applications like automatic meshing or some features that are not available in our software. So that's the only time I program, and I'm very happy with that. So in this presentation, I will introduce you a TICO-TK add-on script for Gridgen, one of our products. And the name is Butterfly Maker. Butterfly is the name of a certain kind of a topology, grid topology. So the way I see the future of the small languages like TICO is the TICO is a small person who's standing on the shoulder of a giant software like Gridgen or other software. And I really like to see that. The Gridgen is one of the leading meshing software in the world, and it has been used by many engineers and scientists since 1984. So it's been 25 years. We're still there. It's a complete toolkit for generate all kinds of meshes with different cell types like structured grid, unstructured, as you can tell in these pictures. It uses a bottom-up approach to generate the meshes. For instance, in this little example here to the right, to create a structured grid for this little cube, first of all, you start with connectors, in other words, curves and lines, and then you assemble the connectors into domains. Eventually, you assemble the domains into block. It sounds really simple, okay? All right. And Glyph is not another small language. It's really a Gridgen scripting language. I would call it a combination of TICO and Gridgen specific commands that are written in C++. It provides a text-based procedural interface to Gridgen's features. In this little code segment here, you can tell all the commands begin with GG : are Glyph commands. Like this one, GG : TK load enabled all the TK commands. If you don't call this line in your code, you cannot run any TK commands. Likewise, the GG : block get all returns a TICO list that consists of all the existing blocks in your grid. So basically, I would say if you look at a Glyph script, as we call it, it's really a combination of TICO-TK commands and a Glyph commands. Oh, I haven't finished this part yet. And all the Glyph scripts can be run either in batch for automated meshing or in Gridgen's user interface. It is extremely useful for all kinds of different applications, but in this presentation, we will be focusing on the last one, which is developing specialized meshing applications. First of all, we need to introduce several concepts. So what is the butterfly topology? Usually we could call it OH topology, like the right picture, the H topology or O topology. The O topology is a series of blocks with grid lines arranged in the O shape or wrapping nature, like a CH or LH. You can see the wrapping nature in here. So the basic types are OH, CH, or LH. There are another two concepts in here we need to mention. The first one is a butterfly phase. The butterfly phase is a block phase where we are going to create OH domains on the phase. Likewise, the butterfly connectors are the ones that will be used for assembling the butterfly phases. So why is this topology so useful for CFD calculations? Imagine right now you're doing a flow simulation in an internal flow simulation in a geometry like this, a cylinder-looking pipe. To do this simulation, you really want very high-quality hexahedrals near the wall region, and also you want very tight spacing in the normal to wall direction. A regular edge topology grid will not give you that. So in the left picture, no matter how fine your grid is, you will always have very bad skewed cells at the corner. And that is because of the topology you're using. It has nothing to do with the generator. To solve this problem, the best solution is to transform this H topology block into an OH topology block system, so that you will always have very good cells at the corner no matter what. So in this block system, you will have a one H topology block in the center and 4 OH topology blocks wrapping around it. And that's our goal. So why do we need a script? The GridGen is a very large meshing software. It has hundreds and hundreds of features, and it's designed for solving the most complicated meshing problem, but still, we would be missing some points here and there because we have a large pool of customers. So apparently, GridGen does not have automatic OH grid topology creation capability. And if you want to transform this topology in GridGen's GUI by using existing commands, it could take hours. And the third reason is one of the most reasons why I am on board, because this is one, I quote it, this is one of the most important features of our major competitors, so we really want to beat them. And this little picture here shows you a simple geometry of a combustor. So as you can tell, there are about 16 little cylinders looking like little blocks running between the inlet and outlet. To transform all the 16, not too much, just 16 blocks into the OH topology, it will take you about 2 hours for advanced GridGen to do that, because it's not really a symmetrical geometry in here. But if you use the script, it will take 1 or 2 minutes. So don't laugh at me because this script is written in 8.3, but I will have to say for the next generation of our software Pointwise, Pointwise will support the TicoTK 8.5, so in the future, the majority of my work will be using the 8.5 instead of 3, so I think Jeff will be very happy to hear that. So this script, I wrote about 1.5 years ago. It was written in 8.3 and Glyph 1.0, which is the first version of the GridGen scripting language. It has approximately 4,000 lines and 50 procedures. It's not a very large script. The main features include the following. I'm really happy to see rows 4 with the stars in front of it, because rows of features which our competitors don't have. So the main features are something like you select a bunch of blocks, and this script will allow users to propagate the OH topology changes through this block system in certain direction, and also it will maintain the connected distribution in certain regions. Because for safety study, it's very important to say, if you would like to have, well, usually you have a grid clustering at the inlet, for instance. And once you create the new block system, you really want to maintain that feature in your grid, so you don't have to do some additional work afterwards. And also the script will allow non-homogeneous scaling for the OH blocks. In other words, once you create the new OH block system, you can scale them. So the H block at the center could be smaller in 3 directions, I, J, or K. The last 2 are designed for more complicated scenarios where you have multiple domains on the butterfly face, or your butterfly face is not a flat plane, it has high curvature, or it has certain kind of slope discontinuity. The user interface is really simple. I feel a little bit embarrassed to show it, but for this case, the TK widget is not really the tricky part. The algorithms are, so I think this one is working fine with me. It has 4 main frames. The first frame to the left is a block selection frame. It allows users to select the blocks in either interactively in GridGen's user interface or in the list box. The list box that displays all the names of the blocks. And these 2 TK widgets are keyed to each other, so it's basically a one-to-one mapping. Once you select anything either in the list box or in the GridGen's user interface, they will be like catching up with each other. And the second frame is propagating direction selection frame. It gives you 4 options. The IJK direction is very easy to understand. For instance, if you select J direction, the OH topology change will be propagated in the J direction. However, if you select all, that's another important feature in here. That means you will put the edge topology block inside of the original edge block. In other words, your butterfly faces or the butterfly connectors will not be sitting right on the original block faces. Instead, they will be inside of the box. The third one is a meshing parameter frame. It allows users to play with the meshing parameters. For instance, the scalar in the ijk direction, so the element will be in the range of 0 to 1, so you can play with it. You can scale your little edge topology, edge block inside. The second one is grid points on all grid ribs. All grid ribs, the way I call it is, they refer to the connectors that run between the inner and outer boundary of the new all grid blocks. The reason we put in here is because it basically controls how tight your spacing would be in the boundary layer. So the more grid points you put in over there, that means you have tight spacings near the wall region, for instance. I think this makes the whole calculation more flexible for the users. The third one, probably you can't tell, you can't see very clearly, is it's a check button, propagate topology check button. And once you check this box, it will actually propagate the topology change in the selected direction. It will be grayed out unless multiple block selection is made and the propagating direction is selected. The button preview topology will automatically create all the internal connectors and the butterfly connectors, so the users can tell what the future topology will look like before you run the entire calculation. This is mainly for the performance concern. And the last one is execution frame. Generally speaking, the main workflow looks like this. The script will first validate the user input, and I believe users usually don't do what they're supposed to do, as everybody knows about it. So actually, this first step, I think, is very challenging for me because I always hope they could do the right thing, but they don't. Then the script will obtain the propagating block list, then determine which domains will be turned into your butterfly domains in the future, and which will be actually maintained in the box. And the three-dimensional scalar will be used for evaluating the location of the center edge domain. After that, the new butterfly connectors and new internal connectors will be created, and the distribution of the new connectors will be calculated, and eventually those connectors will be used for assembling new domains, then the new blocks. The following are several challenges. I think they are kind of worth mentioning here. The first one is user input diagnostics. First of all, we have to evaluate the scaling factor and the grid point number. For instance, scaling factor, the three elements should be in the range of 0 to 1, and grid point number should be integer, and it should be greater than 3. The tricky part in here is actually the third item, is the propagating list valid? In other words, we put in several conditions in the code. Actually, I put in several conditions in the code so that we could tell, we could evaluate whether the list is valid or invalid. For a valid propagating block list, all the blocks, they should be connected one to another. And they should be sharing the full face at the boundary, at the butterfly face. For instance, for each butterfly face, all the domains on the faces will be shared by the neighboring blocks. And the last one is caused by some invalid user input. We should check there is no duplicated block in the list, because imagine in the TK window, the users, they would make some selections, run some cases, and go back and correct the selection, change the meshing parameters. So when they are doing all this, there's a chance that the duplicated blocks will be added into the propagating list in the code. So I added this item here, just make sure we don't do any additional work if it's not necessary. The last one is, are there any temporary connectors that need to be eliminated? All the temporary connectors are created only for the preview, the topology preview. So whenever you update the preview, you have to clean out all the cluttered display window with all the temporary connectors. The universal index system is very important in this application because we constantly look for connectors, domains, and blocks. So this has, this is a big factor that influences the performance in here. The traditional index system is IJK for the structure grid, which makes a lot of sense to me. But the thing is, it doesn't reflect the topology information in the index system, which is very important in this case. For instance, if somebody gives me an index system of IJK, I don't know whether this connector domain is in a center edge topology or is an all-grid topology or something like that. So that one is not very practical in this application. Instead, I created a two-dimensional index system in here so that all the domains in the connector in indices can be represented by two of the following variables. The first three, Indy 1, 2, 3, they stand for either I or J or OK direction. Indy 3 is for propagating direction. So for instance, if the propagating direction is I, then Indy 1 or 2, there could be J or K, something like that. And the fourth one will be used for every single index systems for connected domains. It is either the center or all-grid 1 or 2 or 3 or 4. In other words, whenever I'm looking at the indices of an entity, like shown in the table, I actually know where they are. They could either be at the center or they could be part of the all-grid 1 or all-grid 4, and this is very important. So the little example here shows you how these domains are added into a block face and eventually are assembled into a block. So in Glyph, you call the GG : block begin, and this is for structure grid, and then you add the domains into each phase. So if you notice here, the domains are using the center into 3 or 1 or 2. That means all the domains, they are assembled into a center block. So that's why the first index is centered. One of the challenges is how to locate the H domain by using the three-dimensional scalar. So we prefer to put the H domain in the center part of the butterfly